Welcome to Sundar's lecture. This is lecture number 35, and in this lecture we are going to see design of synchronous counters. And in design of synchronous counters, what we are actually going to see, we are going to design mod 5 counters or mod 6 counters, like that we are going to design using different flip-flops. Before that, what are all the topics we have seen in the previous class? This is the topic we have seen in the previous class, right? Synchronous up counter and then the synchronous down counter, right? So what we have seen, if you give one clock pulse, then if you assume all the outputs are zero, then the output A, B, C is going to become 0, 0, 1. And then if you give another clock pulse, then it is going to become 0, 1, 0, which means it is 0, 1, 2, 3 up to 7. And then again from 7 it goes to 0, right? So it will be counting from 0 to 7 again and again after every clock pulse. And we have also seen what is a down counter and how it is actually working using JK flip-flop, right? So here, if you assume it is 0, 0, 0, the initial condition, if you give one clock pulse, then obviously it will go to 1, 1, 1. And then again it will go to 1, 1, 0. That means 7, 6, 5, 3, 2, 1, 0. And then it goes to 7 from 0, right? So this is what we have seen, and I have shown you a fixed diagram, like this is the synchronous up counter and then down counter, and I have already also told you that how we should give the clock pulse to each flip-flop, since it is a synchronous sequential circuit, right? So in synchronous sequential circuit, the clock pulse must be same for all the flip-flops. At one instant, all the flip-flops will get the same clock pulse, right? And now we need to design now synchronous counter. Let us assume that we are going to design mod 5 counter, right? So what is mod 5 counter? We should know first what is mod 5 counter, which means this counter is going to count from 0. Assume that if the initial conditions are 0, then it should count 1, 2, 3, and then 4. That means if you give one clock pulse, it goes to 1, and then if you give another one clock pulse, it goes to 2, and then if you give another one clock pulse, it will goes to 3, and then 4. And the next step, assume that the outputs are 1, 0, 0, which means we will design anyhow. We need to design that it is a 3. We need to use 3 flip flops. That I will tell you. Anyhow, from 0 to 1, 1 to 2, 2 to 3, 3 to 4, and then if you give next clock pulse, it goes to 0 again. Next 1, 2, 3, 4, and again it goes to 0, and it will continue like this. Can you understand? For example, we need a clock pulse. We need to count only 5 from 0 to 4, and if after that I need to make it to reset 0. That is our idea, right? So first step 1, let us maybe I will explain the design of synchronous counter using using an example to design the mod 5 counter, right? So maybe I will go for now step number 1. Step 1, determine number of flip-flops needed. That is the first step, right? So how will you find this one? Maybe, right? We will have a formula like 2 power n greater than or equal to n, capital letter N, where this n is number of flip-flops and this n is number of states. That means states here number of counts. We can say it as number of counts. And how many number of counts we need here? N, which is equal to 5, right? Because we need to design mod 5 counter, so it will be n will be is equal to 5. And so that what will be the equation now? It should be like this. So how this equation will be now? So what is n? What is n to satisfy this equation? So n must be 3, right? N must be 3. That is the idea. Because if you put 3, then only it will goes to 8. That means this is greater, right? So if you put 2, it will be 4. So number of counts will not match here. So that n, which is equal to 3. So now what we have found, that means we need to use 3 flip-flops. That is the step, right? Okay, fine. Now step number 2. Next step. Step number 2. Choose the flip-flops. Flip-flop. What is the flip-flop we are going to use? Maybe for this example, I'm going to choose JK flip-flop, right? I'm going to use JK flip-flop. That is my idea, right? Next one, step number 3. Step number 3. Here, I'm going to derive design table. Design table, right? That is my idea. Next one, right? So how I can derive the design table now, right? What is the procedure? Maybe you can see here, you have 3 flip-flops, right? So for example, maybe I will just okay, we will see this one anyhow. So we have 3 flip-flops, right? So how many inputs will be there? Because it is a JK flip-flop, you have JA, KA, JB, KC, KB, and then JC, KC. So you have 3 different flip-flops are there. Maybe before that, we try to write the present states now. Let us do that one first. Present state, right? That is the first one. And the next one will be next state. That is the second one. Right? So what is this one actually means, right? So for example, let us assume that I have the first state as 0, 0, 0, right? So if I give one clock pulse, what should be the next state? That is what we have written here. The next state should be 1, right? So if I give one clock pulse, so that is the idea. So what happens now? This has to become 0, 0, 1. And if the present state is 0, 0, 1, right? What should be the next state if I give clock pulse? 2, right? 2. That means 0, 1, 0. Why I am using 3 uh, inputs here or 3 steps here? Because we are going to use 3 flip-flops. If I use 4, then you have to use 4 variables. Try to understand it very clearly. Then if it is 0, 1, 0, then the next state should be what? 0, 1, 1. And if the state is 1, 0, 0, then what should be the next state? Oh, sorry, not 1, 0, 0. 0, 1, 1. What should be the next state? It should be 1, 0, 0. And if the state is 1, 0, 0, what should be the next state? It has to go to 0, 0, 0. Try to understand, because from 4 it has to go to 0, 0, 0. That is the idea. See here, from 4 it has to go to 0, 0, 0 for the next state. Try to understand it very clearly, since you have to be very careful here. So this is 0, count number 1, count number 2, count number 3, count number 4. That means 5 counts, totally 5 counts. At the 5th count, it has to go to 0 again, since we have to measure it from, we have to count it from 1 again. So this is the idea, that we need the present state and then the next state. Can you understand the whole idea now? So what I will do now, I will take the excitation table of the JK flip-flop, so that you can understand it very easily, right? So I will do that. Now you see, I have just taken the excitation table of the excitation table, right? So this is the excitation table of JK flip-flop that we have already seen many times, right? So now what we need to do now, we need to derive the J and then K inputs now. So how many flip-flops you have now? So you have maybe I will just name these kind of steps, right? So because then only you can understand this is QC and this is QB. I will tell you what is this. This is QA, and since it is the next step, so it will be Q plus QC plus 1, QB plus 1, and this will be QA plus 1. That means these are all going to be outputs, maybe, right? So then we will do now flip-flops inputs. Maybe I will just write it like this one. This is flip-flops inputs. So what are all the flip-flops inputs now? So it will be now QC and then JC, that is the third flip-flop input. Then this will be QB and JB, then QA and then JA. Right? So these are all the inputs we need to derive now. Maybe I will tabulate this one so that it will be very easy to write the zeros and ones. So what you need to do now, we need to see this is the present state, right? So this is the present state, next state. So what should be the inputs of J and K? So you have to check for QZ and then QZ plus 1. What is this one now? So that I will get the inputs for JA and KA, right? So I've written wrongly. Right, now I have just changed it. So JCKC, JBKB, and then JAKA. So what is this one now from 0 to 0? So present state is 0, next state is also 0. So what is that? It is 0x, right? So the input should be 0 and then x. And what is the next one? 0 to 0, 0 to 0 again. So it will be again 0x. And again it is 0 to 0, so it is 0x. Check this and then this, because this is QC, this is QC plus 1. It is going from 0 to 1, right? So 0 to 1 means it is 1x, right? So 1x. And then from 1 to 0. So 1 to 0 means x1, x1. And for JB, KB and then JB, so it is going from 0 to 0, so it will be 0x. And again it is 0 to 1, so 0 to 1 means 1x. And this is 1 to 1, right? So 1 to 1 means x0, x0. And 1 to 0 it is x1, it is x1. And from 0 to 0 it is 0x, so 0, this is x. And for the last step, it is going from 0 to 1, so 0 to 1 means it is 1x, it is 1x. And from 1 to 0 it is x1, it is x1. And from 0 to 1, 0 to 1, 1x. And from 1 to 0, 1 to 0, that means x1. And from 0 to 0, 0 to 0, it is 0x. So now what we have actually done, we have just derived the expressions for, the values for J and then K inputs. Now what we need to do, we have to, this is now input now. This is the input, so present state is my input. And we need to derive expression for all JA, KA, JB, KB and then JC, KC. For all the JK flip-flop inputs, we need to draw the K-map and derive the expression. That is the step number 4, right? So what is the next step we need to do? So I will just put like this. Step number 4, derive the equation for flip-flop inputs, right? So this is the next step, right? So what I am going to do now, I will just draw only one flip-flop and I will show you how I am just writing it down. So I will just draw it down. So you can see that I have just drawn the Karnaugh map for this input now from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, and I will tell you what to do with 1, 0, 1, 1, 1, 0, 1, 1, 1, right? So anyhow, so what is this one now? So from for 0, I need to derive the expression for first. I will go for KC here. So this is, I will just show you for KC. For all other inputs, I will just show you what is the expression I'm getting. So first I will go for KC. So what is for KC? So this is the outputs, right? For KC, this is the values, right? So first, this is 0, and then again it is 0. For 2, it is 0. For 3, it is 1. So it has 1 should come here. and for 4 it is x. What happens with the 5, 6, 7 here? See, we don't have 5, 6, 7, right? So it is not necessary to consider the 5, 6, 7 as the care conditions. Those steps, those inputs, I'm not bothered about. So it has to be, what is this one? This has to be don't care conditions. So x, 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 simply, right? So what you can do with this now? So simply, what you can do with this one, I need to cover this one. So I can make this as a pair. That is the only possible. That is the only possible, right? So I will get a pair this one. So what is the expression I will get now? This will be now QB QA. That's all. I've just done for KC. And what is the expression for JC now? So for JC, what should be the expression I'm getting? So it is X, 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 right? Right. This one is 1 for this one. So all others are X here. All others are X. So you can see here, I can consider all these X to be 1 so that this whole becomes octet, right? It becomes octet. For octet, for example, if this is a 3 variable came up, and what is the value of octet? It becomes 1, simply 1, right? So I can do this one. So I will just do everything and I will show you what is the final expression, right? And you can see here, I have just derived all the expressions, right? For JA, KA, JB, KB, JC, and then KC. Right? What is the next step? We need to draw the logic diagram. Right? We need to draw the logic diagram. Maybe I will just put like this so that we can see the expressions too. Step number, what is the step number? I'm getting it to be step 5. Step 5. Right? So step number 5, draw the logic diagram. So how will you draw the logic diagram? So we need 3 flip-flops, right? So 3 JK flip-flops has to be drawn. Any of I will move this one further. I will have it like this so that it will be very easy. I will draw here. So I need to draw 3 JK flip-flops. 3 JK flip-flops. That is what I have got. So first I will write down everything. So make it as JA and then KA. This will be now QA and then QA bar. Right. So next flip-flop. So this is the second flip-flop. I need to draw. So this one will be now JB, KB, 2 inputs, and I will have QB, QB bar. This is the second flip-flop, right? So next flip-flop, third flip-flop, right? So third flip-flop. So third flip-flop. I'm just getting it down. So it will be now JC, KC, this will be QC, and then this will be QC bar. And we know that this is the synchronous sequential circuit, right? So synchronous sequential circuit in sense what? So all the clock pulses, that means for this, this, and then this clock pulses, maybe it is like this, inverted or non-inverted clock pulse, whatever it may be, we need to connect like this. Just connect all the flip-flops. Clock pulses like this, right? So I will just tell this as now CLK, that means clock. So this is synchronous clock, we will give it down. So what is the equations we have? So I will just write it down here. So these are all the equations that we have we have derived. So what we need to do now, we need to connect JA to QC bar. That means this is now QC bar, right? So what you can do now, I can just connect this QC bar with the JA, with the JA, right? So I have just connected. And for KA, I need to give it as 1. So by default, KA must be connected to what? 1. Logic 1, right? And for JB, I need to connect it to QA. JB, I need to connect it to QB. Maybe I will connect like this, right? Sorry. For JB, it is QA. It is correct, right? And for KB also QA. So what I can do? I can connect like this, right? Right? And for JC, it is 1, right? So for JC, it is 1. So 1 minute. So I have made a mistake here, right? So actually, you can see here we were just writing the expression like this, right? From this is present state, this is the next state. So 0 to 0, if it changes from 0 to 0, then J is K is X, right? So now this is JC, this is KC. I have just made a mistake. So you can just change it down. So I will just I will change it down, and you can see here now I've just changed it down. So what happens now? So this expression maybe see here we have made us one mistake and it has changed everything, right? So now this is JC and this is KC, right? Uh, all others are right. All others are right, right? I have just done correctly, derived it correctly, but here these two only will change. So JC will be QA QB and KC will be 1. That is the idea, right? So what we are actually doing, so we need to connect this one now. So for this KC, it has to be given to logic high, it has 1. So I will just write this as now QA, this is now QA, and for this is now QC bar. So everything, every inputs, I'm just writing it down. And what is for JC now? It is QA multiplication of QB. So what we need to do now? Simply draw a AND gate and just connect this AND gate output to JC so that I will get it as QA and then QB. So what I need to do now, simply you have to get it from QA, right? So one input has to be given to QA and another input should be given from QB. Maybe I will just write it as QA. This is QB, right? Now this is actually, and now this is the logic diagram. So where we need to take the output, that is the next question, right? So the output should be taken from QA. So I will just draw it very dark, right? So this is actually the output A. And what is output B? This is the output B, and this is the output C, right? So where we need to see the outputs now? From A, from B, and then from C. Can you understand the concept behind all these kind of steps? So how will you get the outputs now? So you will get it as maybe I will write it here Q Q C Q B Q A. This is the output now. This is the output. Maybe I have just written it as B CBA, and if you give clock pulse number 1 to this circuit, assuming that the all the first states are 0 0 0, I'm just giving a clock pulse at this instant. Now first clock pulse as 0. So now if it is so, then the next state it is going to become 0 0 1. And if I give another clock pulse, that is clock pulse number 1, and from here I'm just giving another clock pulse, so it becomes now 0 1 1. And if I give another clock pulse here, that means the clock pulse number 2, it is going, oh, this is 0 1 0. If I give another clock pulse here, so it becomes 0 1 1. If I give another clock pulse here, it goes to 1 0 0. And if I give another clock pulse here, then it will be going to 0 0 0. Can you understand? So I have just given 0 to 1 to 4, and I am getting it to be 0 0 0. Right, so this is the working principle of this particular modify counter, and you can check it out by yourself. That is very easy to understand too. So we can see it from here itself. So if QC bar is here, then if it is 0, then the output, if this is 0, then this becomes 1. So this one will come here, this one will come here. So obviously what happens to A, for every clock pulse it is going to change from 0 1. Right, you can check it out by yourself. That is very easy. Right, so now we have just drawn the logic diagram of the mod 5 counter, right? So what are all the topics we have seen in this class? See, we have started the design of a synchronous counter. In particular, we have gone to mod 5 counters, right? So designing the mod 5 counters, and what are the steps involved in the designing mod 5 counters? Step number 1, determine the number of flip-flops needed. So what is the formula to find the number of flip-flops needed? 2 power small letter n greater than or equal to capital letter n. What is small letter n? Number of flip-flops. Capital letter n is the number of states or number of counts, right? So we have found it to be 3, and we have decided to have 3 number of flip-flops. The second choice, the second step is to choose the flip-flop type. And in this example, we have taken JK flip-flop. Maybe you can take it the T flip-flop. That we will see in next class anyhow. And the step 3, we have to derive the design table with the help of the excitation table, right? So we need to put which is the present state, next state. With this present state and next state, we need to derive the flip-flop inputs. And then step number 4, we need to derive the expressions for each inputs, right? That we have derived. And finally, with the help of the inputs, we have just drawn the logic diagrams, right? So this is how we have formed. So thank you. We will see mod 6 counter using T flip-flop in the next class.